Anand Subir's fourth lecture. So
Okay, well, thank you. So Suchitra gave a very nice survey of some very beautiful experiments, and perhaps now you appreciate the complexity. So some of the models that I've been talking about here are really my attempt to talk about the very simplest models in which you can get some of this physics. So I talked about in my first two lectures about a Fermi surface coupled to gauge field, because that's really the simplest model we have in field theory of Fermi liquid breakdown. It's probably not directly related to anything Suchitra talked about, but it's a start. And then today I've talked about this model on the honeycomb lattice, which is even simpler, because for one important reason, it doesn't even have a Fermi surface. So we have this Hubbard model with coupling u and t at half filling, and then at small u you had the Dirac semi-metal with just a Fermi point, and then at large u you had a gap. And so this is then one of the first models we can study and really fully understand at some level of a quantum critical point leading to breakdown of Fermi liquid behavior. So what we saw was that here there were sharp quasi-particles everywhere in this phase, and here also there were sharp quasi-particles, although they're gapped at these dispersion points. But precisely at this point, because of the anomalous exponent eta of this Gross-Novak conformal field theory, you had breakdown of quasi-particle excitations. It would be really nice if somebody eventually, perhaps in cold atoms, could do an experiment on a system like this, but we are just studying it as the simplest example of quasi-particle breakdown. So then I started talking about what would happen if you sit at this point and raise the temperature. So the first thing we computed was the conductivity right at that point, and we just did a very simple one-loop calculation of Dirac fermions, computed the one-loop diagram, got some transverse current correlation function, and then computed the conductivity for the Kubo formula, and at the end of the day, you get sigma of omega is frequency independent at zero temperature at the quantum critical point, and equal to this value in units of E squared over h bar. And as I mentioned, this is the value that's been measured, in fact, in optical conductivity experiments on graphene. Okay. Sorry. Yeah. So this is the value in the Dirac metal phase over here, and that's where it's been measured. Right at the critical point, I'm sorry, you get some other number. It's still believed to be by scaling arguments to be frequency independent, but some other pure number, which is the analog of the level of a Kac-Moody algebra, but now of a CFT in 2+1 dimensions.
frequency independent, basically at zero temperature.
This is zero temperature. Okay, absolutely. So this is all at zero temperature. And okay, so now the next question to ask is what happens at finite temperature. So we're going to go back to this point and raise the temperature. All right, so the first calculation you do is exactly the calculation I just showed you. The only difference would be when you do the loop integral, rather than integrating over frequency for one of the components, you sum over it. Okay, seems like a very mild thing to change. So you do that, and I won't show it to you. It can be done, and then finally you analytically continue to real frequency, and that's the subtle part. But if you know your mathematics, as I'm sure all of you do, being string theorists, you will get this answer, although you may not have met analytic continuation before. So this is the answer you get. Remember, previously I had an answer 1/4. That's the answer now at omega much greater than temperature. So when omega is very large, then this tanh becomes 1 and you get 1/4. On the other hand, when omega becomes very small, this changes as a function of omega over t, but even more interestingly, you get a delta function whose coefficient is proportional to t, so that was not there. So the frequency dependent conductivity now looks something like this. It's got a delta function at zero frequency, and then it goes up to the 1/4 value as omega goes to infinity. That's the one loop answer. And now the delta function, actually, what is it due to? Well, it's naively what you would have expected if you had free particles. So if you have free fermions, then at finite temperature, you're exciting a bunch of them, both electrons and holes, since they are particle hole symmetric. You apply an electric field, The electrons move this way, the holes move that way, but their current is both going that way because they carry opposite charge. So they have opposite charges and opposite momenta, but they have equal current. So if you apply an electric field, the currents of the electrons and hole keeps going forever, and that's why you get a delta function. So it has infinite conductivity. Okay, so now the question is this robust? Is this the actual answer? Something rather strange now. You've got an infinite conductivity. And if you think about it a bit more, you realize it can't be the final answer. So you have electrons moving this way and holes moving this way at very low frequencies here. And now they collide. And when they collide, they can come to rest, and there's no momentum left over. So basically, eventually, the net current has to go to 0. And because the current has to decay to 0, the actual conductivity should be 0. Finite. So what you expect is that this delta function is not really a delta function, but it's actually some kind of Lorentzian, and then eventually you go over to the tanh omega t answer at high frequency. So if you do a more careful calculation of 1 over n expansion, you do indeed find by using a Boltzmann equation that that's what happens. But you find that this peak is now of order n. So n is going to infinity, remember. This is really sharp and really narrow, and you get this very strange, sharp result at low frequency and this is not done in a bare 1 over n expansion, as you could imagine. If I just did naive 1 over n, you won't get it. You have to then see, I have to sum a whole subset of graphs and that's what the Boltzmann equation is. So the Boltzmann equation you can view as some inspired guess on how you understand the transport properties of weakly interacting particles. So in the large n limit, these are weakly interacting particles at some level. They're not really particles to begin with even, because there was no delta function pole in the Green's function. But you treat them like particles, and then you assume that the Boltzmann approximation is a good one. And okay, for very large n, it probably is. We don't know for sure, but small n, we're not at all sure. Is this the right way to think about the conductivity? So this is the kind of question which involves, transport and dissipation at finite temperature of excitations that are not particles. That's exactly what ADS-CFT is designed for, in a way, and does best. Much better, I believe, than the Boltzmann equation.
But you also didn't need to put in any impurities because...
Correct. Yeah, so this is the one case in which you don't need impurities because you're particle hole symmetric. So for conformal field theories, when you're exactly the conformal point, you do get a finite conductivity, which is non-zero. So now you see there are two different conductivities. There's the zero frequency conductivity, which is some number of order n in the vector large n limit, and the high frequency conductivity, which is of order 1 in the large n limit. And that's another reason the large n limit is no fun, because it's not uniform in frequency. Some regions of frequencies of order n, other regions of frequencies of order 1. You don't like that. So that's another indication of the fact that the frequency going to 0 limit and the n going to infinity limit do not commute. So it's highly non-uniform. And that's a very generic feature of all vector or epsilon expansions of transport properties of conformal field theories, like this critical point. And the conformal field theory is something we're studying, not because Suchitra has a conformal field theory. It's the simplest theoretical model we have of anything that doesn't have particle-like excitations. So it pays to study it well.
If you were in n equals 4 Yang-Mills,
yes,
and at weak lambda,
yeah,
then presumably that width would be controlled by lambda instead of 1 over n squared there. And
sure.
And you wouldn't have this.
Weak lambda. Let's see. Yeah, so that's somewhat like an epsilon expansion. I think that's correct.
And then you wouldn't have this hierarchy of.
No.
There would be an overall n square outside. Just lambda would control everything.
Well, I'm going to argue that even for strong lambda, that's true for super Yang-Mills. That's a matrix large n limit. It has a very different character.
But even at weak coupling, you would see that.
Sure, in that case you would see, but there it's physical and you expect it.
Yes.
Yeah. Well, we're not okay, I think so, yes. If you believe the Boltzmann analysis, which probably is right. Okay.
How much do you know about this function sigma?
So in the large n limit, we know this whole shape of this thing. It's not exactly a Lorentzian, it's some universal function. We have a whole chapter in my book is about computing that thing. Written 10, 15 years ago. Okay.
It doesn't look Drude like it at low frequencies.
Well, approximately. It's approximately Lorentzian, but not exactly. You can compute the whole thing. It involves solving an integral equation, which takes a few days on the computer, but it's almost a Lorentzian. It's some complicated shape.
1987.
Yeah. In fact, I redid that calculation last year because of various reasons. Anyway, so before I jump on to how holography addresses, let me give you just yet another example which has almost the same physical issues, but for bosons. So we're considering now, I started with Hubbard model of electrons on the honeycomb lattice. Now I'll talk about Hubbard model of bosons on the square lattice. And then finally, if time permits, I'll talk about the elephant in the room, which is the Hubbard model of electrons on the square lattice, which the closest to anything that I talked about. All right, so if I take Hubbard model of bosons on the square lattice, then there is also a quantum phase transition between a superfluid where the bosons are condensed and a mod insulator where the bosons are trapped, one each in each site. So that's an experimental realization of this kind of model where again it's the same thing. There's a hopping T and a repulsion U. Let's assume the chemical potential is such that your density is 1. And now these are Bose operators. That's it. So this model, very similar to the honeycomb lattice electron model, had a transition again from a metal to an insulator, accompanied, because electrons carry spin, accompanied with a transition from paramagnet to antiferromagnet. All of that happened at the same point, at least in that simple model. Here there's no spin to worry about. There's only charge. And bosons can't form a metal, or they can form a superfluid. So you have a transition from a superfluid to an insulator. And this is also turns out to be relativistic field theory for somewhat related reasons. It's because your vacuum state, which is the insulator, has one boson per site. And that vacuum state at integer density has equal numbers of particle and hole excitations. So we can think of this as an electron and a positron, and the vacuum is one particle per site. So because of that particle-hole symmetry, you want a theory where the number of particles and number of holes are the same, and that turns out to lead, and I won't go through the derivation, to lead to a relativistic field theory, but the idea is very similar to what we went through in somewhat more detail for the honeycomb lattice. And in fact, this is exactly the field theory we already met, except there's no fermion. It's just like the antiferromagnetic autoparameter for the honeycomb lattice with 3 components. This is just the O2 model, 2-component psi-force field theory. So this field theory then has a transition at some critical coupling from a superfluid to an insulator, and now I can just turn the crank just like I did for the honeycomb lattice. So I have a CFT3 there, and then I have where quasi-particles break down. I have this quantum critical region, which is described by the CFT3 at non-zero temperatures for a 2-dimensional system. And if I want to think about transport in this region, it's really the most important property of it is that the characteristic time at which particles collide with each other, and this is also true for the honeycomb lattice model, is basically given by h bar over kT. Now, some of you in gravitational physics may know that there's a very similar time, which are ring down times of black holes, which is again h bar over the Hawking temperature times numbers like 1 over pi and so on. And that's not an accident. That's because, as we know from ADS-CFT, it's the horizon that controls relaxational processes, and this is the characteristic time of relaxation of this strongly interacting field theory. So this leads to, as I've already discussed, a universal conductivity, and this should be viewed as the exact analog of the KSS result, that the viscosity to entropy ratio is h bar over kb. Of course, they put both of these equal to 1, and the universal constant, which they say is 1 over 4 pi for super Yang-Mills, well, it's generally some other number, and even for this Bose-Hubbard model, it will be some other number here. Analog, probably close to 1 over 4 pi. And that's one of the reasons for, but we don't have any computations of it. It's very hard to compute. So let me just fly through the same reasoning I just applied for. So if I compute the conductivity, I'll get the same sort of results. I'll get a frequency-independent conductivity 0. Yeah.
Did you say it was close to 1 over 4 pi?
We don't know. We don't
Oh,
know.
you don't know.
We don't know. No one's measured it here.
But they could.
Hold on for a few more years. I think they will try. They're just now getting the 2D critical point characterized in Bose's Hubbard model. Yeah, I think there's some exciting stuff going to come along. I hope. Anyway, so if I compute the conductivity, just like a honeycomb lattice, at this point I'll get a constant number. It's not 1/4 here, it's some other number, 3/pi or something, I forget. For bosons, for Dirac fermions, it's 1/4. So there's no supersymmetry for sure. and then when you raise the temperature, again the same story happens. You get a delta function at 0 frequency telling you about these collisionless particle and hole excitations, which I showed you some pictures of. And then to figure out what happens as these particles and holes collide, you write down a Boltzmann equation. But let me take a much simpler point of view. So this is some fluid of particles and holes flowing in the net, flowing around. They collide with each other at some collision time and respond to the external field. So let me write down the very simplest equation of motion. You solve this for V and then compute the current. This is the usual formula. This is the so-called Drude formula that you see in the very basic analysis of Brownian motion. So we're just imagining these particles are colliding and undergoing Brownian motion, and you get this kind of term with this collision time is h bar over kt. So if I take and this is something I already discussed, so if I take the real part of that and plot real part of sigma of omega, so this is without collisions at one loop. With collision, this is the kind of curve you expect again. Some high frequency conductivity, which is the analog of the 1/4, some Drude like peak with a width of order of 1/tau collision. So that sounds very reasonable, and okay, maybe that's the answer, but we don't know this is correct, if this frequency dependence is correct, because it's never really been measured or computed numerically, because it's really hard to look at things at real frequencies at low temperatures numerically. But let me give you an argument why this might not be the answer. So that whole process of thinking in terms of particles and holes and moving around, that's great in the insulator, because those particles and holes actually exist in the insulator. But right at the critical point, they don't even exist. So what right have I to write down an equation of motion of an object that doesn't even exist? That's really what I'm doing. And that's what the Boltzmann equation is doing. But the implicit assumption is that this large n limit is actually good, because at n equals infinity, they kind of do exist. But beyond that, they don't. But equally well, I could have said, wait a minute, why do you want to talk in terms of the particles and holes? Let's go to the other side. Let's go to the superfluid and ask what are its excitations and approach the critical point from that side. What will you get? That should be a perfectly equally legitimate procedure as what I'm using here. So what are the excitations of the insulator? Well, they are vortices and anti-vortices in the superfluid. Excitation of the superfluid are vortices and anti-vortices. Insulator are particles and holes. So there's a vortex and an anti-vortex. This is a point in space-time. And so I can really write down a dual theory, and literally you can do that. This is mirror symmetry of string theory. There's a particle-vortex duality, and you get a dual theory of particles and antiparticles, which are vortices and antivortices, interacting, in fact, in that case with a gauge field, which would be the description of the superfluid phase. Okay, so I could equally well start with the vortices and antivortices and write down a Boltzmann equation for their collisions, and therefore compute the conductivity. Okay, so nobody's really done that, but you can guess as to what the answer might be if the proper description was weakly interacting vortices and antivortices. Well, there's one very basic relation, which is the Josephson relation, which tells you what a moving vortex is. Now, if you're moving particles, moving particles create a current and they respond to an external voltage. A moving vortex, as Josephson taught us, creates a voltage in the transverse direction. So in fact, roughly speaking, there's a duality that when you talk about transport of vortices, voltages and currents exchange positions. So if you think of vortices as particles, the resistance of the vortices is actually the conductivity you would measure in the laboratory. That's actually an exact duality you can prove for this kind of field theory. It's very closely connected to dualities in Chern-Simons gauge theories and mirror symmetry. That's almost an electromagnetic duality in ADS4 in 4 dimension. These are all connected to the Josephson relation connecting change of phase to voltages. Anyway, so that's really all I need. That these particles, these vortices, are moving around, colliding with each other, and if I compute their resistivity, that's going to be the conductivity that I'm going to measure. Okay? So if I take a vortex point of view, this is the particle point of view. You have a Drude peak of particles and then something at sigma infinity. But if I took a vortex point of view, I should get this, because in vortices, I will predict the same answer for the vortices, but for the resistivity, not the conductivity. So I invert it, and this should be the answer for vortices. Question? Yes?
So you do have a difference. On one side, it's a gapless system.
Yes. Well, we are approaching a gapless point in different ways. Correct. So there is a difference, which is that these particles have short-range interactions. These vortices have long-range interactions. That's correct. But you're at finite temperature, all those interactions get screened anyway, so it's not clear. Okay. So really, we come down to depending on which 1 over n expansion I do. You can also define a 1 over n expansion for the vortices. With one particular 1 over n expansion, this is your prediction. With the other 1 over n expansion, that's your prediction. All right. So what is the answer? So now you start taking bets. Is sigma of 0 bigger than or smaller than sigma of infinity? Does the shape anything look like this, or does it look anything like this? These very basic questions we are not able to settle by the conventional epsilon of 1 over n expansion of condensed matter physics for this very simplest interacting CFT3. Okay, so this is what drove my interest in ADS CFT in the very beginning. Yeah, this question.
What's the relationship between a tau EQ and a tau C?
Roughly the same at this order. Yeah.
So you still expect the kind of
yeah, x bar over kt, correct. I just wrote these slides at different times, and so I'm sorry, I apologize. I should have used tau c everywhere. Tau eq is a better defined quantity. It says it doesn't refer to any collisions of particles that don't exist. It just says take a system, disturb it from equilibrium, and watch how fast it takes till it comes back to equilibrium. It's a better defined. Tau collision, okay. If you had well-defined particle, it's clear, but if you don't, who knows what it is. Okay, so let's do holography. All right. What does holography have to say about this? So this is the very simplest holography. This is ADS4. So the dual of any such theory, of any conformal field theory at some level, is in a background which is ADS4. And at finite temperature, we just make the approximation of describing it by the Einstein theory, in which case you'll get a Schwarzschild black brane in ADS4, and the temperature of the black brane will correspond to finite temperature of your quantum critical system. All right. So let's go ahead and do the very simplest computation of conductivity in this theory. I think many of you in your talks yesterday talked about far more complicated calculations, but this is the most basic calculation. So you have a global U1 charge. So you put in the Maxwell term. Now there's no charge density. So this is just a perturbation. It's not going to change ADS4. ADS4 is fixed. The metric is ADS4. We're just doing linear response in this charge density. Okay. So you go ahead and compute it, and let me just tell you what the answer is. So this is the analog of the one loop answer. Okay. So, or the 0th order answer. So let me make a table here. So on this side, I'll say field theory. And here's holography. So free fields, we got sigma of omega. This is free fields. You get a delta function at 0 frequency and something So something very singular. And here, with colliding particles, with collisions, if there are colliding particles, they will look like this. And if they're colliding vortices, they look like this. Could be either. Okay, what does holography give you? So let's look at the very simplest theory. This is M theory, n goes to infinity. That's precisely what you would do if you're doing M theory on ADS4 cross S7, and you just did linear response. You would get exactly this theory, and this E squared is a number you can compute. So E squared turns out to be of n to the 3 halves. 1 over E squared is about n to the 3 halves, with some pi's and square root of 6 and so on, all related to the volume of S7. So E squared is just a pure number. Notice this is in 4 dimensions, where E squared is dimensionless. So that's a pure number. You can go ahead and compute it, and from this you compute sigma of omega, and what you find is just a constant, basically equal to 1 over E squared, if I remember, or E squared. I don't remember. So very different from either limit. So in the large n limit, the pure answer gives you just a constant. And so this was very puzzling when you first saw it. What does this mean? There's no delta function at 0 frequency. Even at finite temperature, it's a constant. So here, of course, it was initially you're misled. This is a constant, but it's only a constant at 0 temperature. If you go to finite temperature, you get all the other structure. Here, it's a constant even at finite temperature. So in some sense, you should think of this M theory as the exact polar opposite of free particles, because there's no delta function at 0 frequency, and this is the very, very singular dependent frequency. There is no dependent frequency at all. And why is it a constant? Well, it turns out to be a constant for a very simple reason. It's related to the self-duality of free Maxwell action. So this theory has a E goes to B interchange, and you can show that implies sigma of omega as a constant. So there's several pages of arguments in this paper where you can see how that follows. And what is the self-duality between E and B in this theory? That's in fact precisely the particle vortex duality, or mirror symmetry, for the CFT 1 dimension below. So this is an observation by Witten a long time ago, that S duality in 4D becomes mirror symmetry in 3D when you connect them by ADS CFT. I'm paraphrasing some complicated things I barely understand. But anyway, that's sort of what happens. You get so that S duality of this theory, or just as the E goes to electromagnetic self-duality, gives you a frequency-dependent answer, which is just equal to this coupling. Okay. So, yes?
How much of this is just tied to supersymmetry?
Sorry?
How much of this is tied to supersymmetry?
It's not tied to supersymmetry at all.
So if this was a non-supersymmetric four-dimensional gauge theory, you would have strong dynamics. You don't have to worry about. You couldn't treat it this way.
Well, I mean, the only approximation I'm making is just ignoring all the higher order terms. I'm taking linear response, and I'm ignoring the fluctuations of the metric. So it's an exact treatment of the 4DC. I mean, it's a free CFT.
This is Maxwell. So
This is Maxwell, correct? Yes.
That's,
Yeah. There's only one global U1. So certainly, and also in the large n limit, all the U1s just separate from each other.
Even if it's non-abelian, there's no strong dynamics.
Yeah.
Everything gets cut off at the ADS scale.
This is on an ADS4 background. Yeah. This is the, okay.
So you say it's perturbative at the effective lambda QCD of the non-supersymmetric Yang-Mills theory?
Anyway, well, okay. I'm treating it as a classical theory with a factor of n out front, if you wish. So some effective gravity theory on anti-de Sitter space.
Yeah, I mean there is an effective IR cutoff, which I think is what David was saying in the
Yeah.
in the thread.
exactly.
But you have strong physics at that scale, though. You don't have to
No,
worry about
well,
that scale.
okay. We know the physics at short distance of the CFT, which we fully understand. I mean, we understand the structure of it. And this is just some regulation that, this is describing the crossover to what happens on the scale of the horizon. That's where all the important physics is coming in. And the approximation we're making is we're throwing out all the dilatonic fields and everything else, and just focusing on just linear response in the electromagnetic field. So, but we tried to go beyond it, and that was done in collaboration with Rob Myers and Ajay Singh. So we treat this as an effective field theory. This is some effective field theory in holographic space, and we said we want to work to second order in F. We don't really care about all kinds of gradient terms that change the metric because we're just doing linear response anyway. So we just looked at all possible terms which are second order in F and which had 4 gradients. So this had 2 gradients, and so you want to look for 4 gradient terms. And after some various field redefinitions and using the fact that you're simply doing linear response, you can reduce everything to 1 term, or at least Rob Myers and Ajay Singh showed how that could be done. So when you have another term, just like any effective field theory, you get a parameter gamma, which is now a free parameter. So E squared, you can think of as something that now you have 2 parameters, E squared and gamma. Okay. So here's another theory. You just do the usual calculation of the conductivity by solving the equation of motion with this additional coupling. And then what you find, and this is the result. Okay, so at gamma equals 0, you get the constant that we already have. And one thing you find also is that even for non-zero gamma, the sigma of infinity doesn't change. So you can view this value, and this is really, this is sigma of omega divided by sigma infinity. So this value here, and sigma infinity is not a function of gamma. So the high frequency value is actually independent of gamma. So you can say that I can fix E squared by computing the high frequency conductivity, because that's what determines the value over here. So this means that, and even, in all of these theories too, nothing much happened at high frequencies. So the one possible idea is then you could take this value at high frequency compared to temperature, whatever that value is for your favorite critical point, and use that to fix E squared in this effective field theory. So now you have another coupling gamma, which is free. That's fixed because you fixed it to match the high frequency value, which you can compute by other methods. But what you find is that consistently this theory requires gamma less than 112. And to me, that's really the first sign that this is making some sense. Because, compute gamma at the maximum possible value, you get this red curve. And of course, it's really remarkable that that looks like a Boltzmann result for particles. But now it's just a very tiny peak, it's not a big peak. And the shift in the zero frequency conductivity from here to there is about 30%. Okay, that's some indication that to me, that's the first indication this is something, you're on to something. I don't know, maybe we're not, but it's telling you that these corrections are bounded. They're not huge. The factors of 4 pi could have easily have worked out that was 10, but it doesn't work out that way. Yeah.
There's some sum rule though. So once
No, there is no sum rule. So CFTs have no sum rule because they have an unbounded spectrum at high frequency.
okay, so it's very non-trivial that the shape looks.
Yes, absolutely. Yeah. And for negative gamma, you get the value you would have thought if you had a system, whoops, wrong direction, with vortices. You had the dip as you expected. So this picture, of course, I drew anticipating the result. In fact, I only do these pictures after we knew this answer from ADS CFT. Then we, came up with a way of thinking about it. Although we could have before, again.
Did you understand the signs? Why one gives vortices and one gives?
Well, the sign of gamma itself, do we know what it is?
No, can you understand in some other way why picking gamma, say, positive would make it look like particles on the boundary rather than...
No. So just this calculation. But there is another calculation that we should be doing, which will shed light on that question. Yeah,
I was just going to ask, the high derivative terms that you add, if I start in 11 dimensions
yeah,
and dimensionally reduce to obtain that
yes,
low energy effective action,
yeah,
then does that high derivative term come from the high derivative terms in 11 dimensions?
I believe it does. Yeah, there's many terms come.
But the point is, those but they're fixed.
They're fixed. So
the
they're fixed.
coefficients are entirely fixed.
Absolutely. So you take your favorite CFT, all those terms have entirely fixed coefficients. Correct. Oh, I absolutely agree. So my favorite CFT is the Bose-Hubbard critical point, and we have to fix gamma. For this to have predictive power, we have to fix gamma. If you take M theory, you can probably compute gamma. I think that's reachable. To string theory, you could probably figure it out.
Gamma was the parameter in front of that hydrotic term.
Correct. Okay, so that takes me exactly to my next point. So anyway, I've told you that that's the vortex. So it's really, I think, quite striking that you get results that you might have expected from this dual picture of particle vortex transport, and you get very different physically looking different answers. And this is the kind of thing that I would optimistically say the next few years will be tested in experiments on numerics or something. Is it going up or is it going down? That kind of thing. Right, and this is the maximal range. That's another nice thing. Of course, it could be you included the next term and you get even bigger terms. But, I like to draw the analogy with Wilson-Fisher's expansion. Now, Wilson-Fisher theory for the critical phenomena in 2 + 1 dimension was an epsilon expansion down from 4. Of course, epsilon is 1, but they assumed epsilon was 0.1 and they did some calculation. And why did they believe it worked? Well, you don't really know it's going to work, but when they computed the exponent eta, they found it was epsilon squared over 24 or something like that. It was at 24 that gave them confidence, yes, this is going to work at epsilon equals 1. So here, this 1/3 gives me some confidence here that this is perhaps converging in some sensible physical way. Not the fact that n is 1 here, I'm coming from n equals infinity of some complicated matrix model. All right, so to point of gamma. So what everyone seems to have agreed, there are two coupling constants, E squared and gamma. So E squared we can agree to fix just by sigma of infinity. And that we can compute. That's a 2-point correlator.
Sorry, can I come back to that? Because, you mentioned there was this sort of electromagnetic duality.
Yeah.
Actually invert the coupling there.
Correct. Well, approximately. For small gamma, this is the negative of that. So gamma goes to minus gamma. So under particle.
That inverts E as well.
Sorry?
That invert E as well.
Invert what?
E, the coupling constant.
Yes, it does. It does. Yes. So gamma changes sign under electromagnetic duality, at least for small gamma.
All right.
So at n equals infinity, gamma has to be 0 because the theory is self-dual. But even M theory, I've asked many string theories, is not believed to be self-dual for finite n. So M theory has a preferred sign of gamma. I don't know what it is, but it would be interesting to compute that. It's a 1/n correction.
But gamma must come from.
Okay, what is gamma related to? This is
come
what.
From the hydrotic terms in.
Yeah. So what gamma is related to is an OPE of the stress energy tensor with current. This is what needs to be worked out. So you take your CFT. So the idea here is that you do some effective theory for hydrodynamics. Let's make an analogy with the Boltzmann equation. How do we do the Boltzmann equation transport? We first assume particles. We compute the collision of two particles. You get some cross-sect T matrix. And then you put that in the Boltzmann equation. Here, we first assume a CFT. We compute all the OPE coefficients of the CFT. And we take those OPE coefficients and put them into the effective theory on ADS. And then we do hydrodynamics. Okay, so that's the parallel procedure you can imagine for CFTs that you extend the particle picture of Boltzmann. So what we need to do here is to compute a zero temperature OPE coefficient, which is this TJJ coefficient, and that will eventually fix the value of gamma. So that's my program for the summer. So
that's from the CFT side. I think what I'm saying is, if you were to do this starting in 11,
yes,
you're imagining that you do some compactification.
Yeah.
Then I get some coupling which is associated to that.
Yeah.
Then you've got hydrotic terms which are given to you by M theory. But then the point is, if you want to do the EM, the electromagnetic joule, when you do the compactification, you should do something like a Kaluza-Klein monopole thing.
No, I don't think so. The
and
dual
then
is very
the
simple.
magnetic joule from that side.
Well,
and that will change what you'll have in your hydrotic term.
Okay. So I agree. I agree that the theory is not self-dual, and gamma just doesn't simply go to minus gamma. There's a very nonlinear transformation of gamma under this duality. But M theory has a preferred frame which breaks the duality. There is no self-duality. In fact, the only theory that's self-dual is M theory.
No, but it's not. The point is, it's not self-duality. You're doing a Kaluza-Klein reduction, and then
Yeah.
you're asking the question: how do I see four-dimensional S-duality from Kaluza-Klein theory?
You don't have such a duality.
You do, because
You only have it at gamma equals 0.
duality, and you realize that from when you do
No,
an ordinary
no.
Kaluza-Klein compactification.
There is no dual. The duality. This action is only self-dual for gamma equals 0. So, and gamma is non-zero for M theory. There is no duality. It's an approximate.
The U one's part of an SOA, so you can't actually do the non-abelian S duality. But you don't have to have the M2 brane theory. This could
I've
be
just got U1.
Yeah.
Let's discuss it.
But anyway, just to also make one more remark, which is, I mean, the CFT here is super Yang-Mills, and of course I can't compute with super Yang-Mills. I just do supergravity and get these terms. If I wanted to actually do a computation CFT, which I believe I can do at least for the Bose-Hubbard model, because I have a field theory there, I have to compute this rather complicated OPE coefficient for the Bose-Hubbard model. That's what we're trying to do right now. Yes, question?
Yeah, wouldn't there be E dot B kind of term?
So I'm assuming there's parity preserved here, no Chern-Simon. I mean, you can extend all of this to that, but we haven't done that. Okay, I guess I've already said all that. All right, so let me just conclude. Okay, good. I'm doing all right. So as far as conformal field theories are concerned, we don't need to give any excuses for using ADS because it really was designed for that. And it gives you new solvable models like M theory for which have strong diffusion and transport and quantum critical crossover. And the value of the solvable model is that it's as far removed as you can get from the Boltzmann picture of transport as you could imagine. So it's the dual of Boltzmann, and it's very useful to have this strong coupling limit. So we're trying to move away from the infinite coupling limit and do something more realistic. And as many talks have already pointed out, in addition to the frequency-dependent transport I discussed, there's a lot of interesting issues in nonlinear, non-equilibrium transport, which cannot be at all addressed even approximately by these field theory methods, even though critical exponents you can't. So the strategy for the future I'm proposing is some kind of hybrid approach where you compute things that you can in field theory and sort of match them to the effective field theory you get from ADS and see how it works. Okay, that's the end of this discussion anyway. Questions? I had like a few slides where I want to finally touch base with some of the things that Suchitsa talked about, if you don't mind. But I pause here for questions on this. Yeah.
In the conductivity computation, the black hole is not charged.
Correct. Here, this is just it's just a Schwarzschild black hole.
So I guess if you compute eta of s, shear viscosity of entropy
It's
density.
1 over 4 pi. That's the we just have 1 over 4 pi. Now, the higher derivative corrections lead to corrections, and Rob Myers is one of those who worked those out. Yeah. That's why I contacted Rob. I said, you got to do them here too.
But why is it so hard to simulate Bose-Hubbard model? It's just tuning away.
So it's not so hard to simulate the Bose-Hubbard model at 0 temperature and compute any thermodynamic property you want. But suppose you could do it even at finite temperature. But what happens is the key thing is you're simulating it in imaginary time. All right, so if you do it in imaginary time, you can compute the conductivity, but you get the conductivity. So this is the frequency complex plane. The imaginary frequencies are 2 pi t, 4 pi t, 6 pi t, and so on. You do the computation in Monte Carlo, you get some value, you get a number here, you get a number here, you get a number here. What you want is the value here as omega over t goes to 0. So you have to analytically continue some function at these points to something on the real axis at very low frequency. Now normally you can do that by sending temperature to 0. So you make your temperature smaller and smaller and you shrink these points. But here you can't do that. You can shrink temperature, but this scale also shrinks. So since your scale you're interested in is temperature itself, going to lower temperature in a quantum Monte Carlo doesn't help you. Higher precision may help, and there's these special algorithms, these worm algorithms and so on. So people are trying. I know that Prokofiev and Lodya-Paulette and Munich are in fact, they said they're optimistic they will succeed in analytically continuing this to the real axis. But It's still state-of-the-art numerics. Maybe it'll be done soon. But if I wanted, say, the, I don't know, any other like the high-frequency conductivity, or I wanted the compressibility, or the exponent nu, or the exponent eta, no problem. You can get it to 3 or 4 significant figures. It's just these transport non-equilibrium properties are very, very hard to get from quantum Monte Carlo. Whereas, the beauty of ADS-CFT is it's designed precisely for real-time questions, as many people have also mentioned earlier. Okay. All right, so any other questions? So I thought I'd just say a few words, since I have your ears, to finally connect up to something more, that you heard about from Suchitra. So I talked about the Hubbard model at half filling on the honeycomb lattice, and this gives us gross no critical point. It's all very nice, and I showed you all these transport properties of models like this, and this was the kind of phase diagram where you had antiferromagnetic order and a gap, and no antiferromagnetic order and Dirac semi-metal. So let me take exactly the same model, and even at half filling if you wish, and put it on the square lattice. That's the only change I'm going to make, and as you'll see, that changes everything. Well, not everything. So the one thing it doesn't change is if you take large U over T, you do get the antiferromagnet. Now, of course, a lot of the things that Suchitra was showing was as a function of doping, but let's keep life simple. You get similar issues at half filling as a function of U over T. So let's imagine I'm changing U over T. That's like adding pressure or something. But the phase diagrams look similar in many experiments, so good enough. All right. So I'm going to large U over T, I get the antiferromagnet, which is an insulator. So the spins are localized at half filling and form this checkerboard pattern, just like on the honeycomb lattice. And this we know for sure on both lattices. It's definitely what happens for the Hubbard model. So what about small U over T? Now there's a big difference between the honeycomb lattice and the square lattice. Here you get a Fermi surface. On the honeycomb lattice, you got these Dirac points. You get relativistic fermion spectrum with Dirac points. That simplified life a lot. Here you get a Fermi surface. You don't get a point zero, you get a whole line zero. Actually, to get this kind of shape, you need second neighbor hopping. Sorry, so it's not just nearest neighbor hopping. There's some anomalies. If you're exactly nearest neighbor hopping, then you get the strange looking shapes. But let's take a generic hopping. The important point is you get a Fermi surface, which is a metal. Okay. So one side antiferromagnetism, insulator, the other side metal, not a semi-metal, and no antiferromagnetism. Okay, not so bad, looking similar to the honeycomb. So let's do the same song and dance we did for the honeycomb. So what we did for the honeycomb, to connect these two phases, we said, let's take this coupling, write it at S squared, and then do a decoupling and introduce a new field phi, which is the antiferromagnetic order parameter. Okay, let's do exactly that. I have the field phi, for which I write down, I'm calling it phi alpha rather than phi a, sorry about that. I write down some Landau-Ginzburg theory for phi. I have some dispersions for the electrons. Now this is some complicated dispersion. It's not that complicated, just a dispersion that has a Fermi surface. It's not Dirac fermion. That's the most important difference. And then I have this Yukawa coupling that couples the spin of the fermion C dagger C to phi. And I've gone ahead and now made phi the antiferromagnetic wave vector, where this k is pi pi. That's the thing that oscillates on the sublattice. Plus 1 on e to the I k dot r is plus 1 on one sublattice and minus 1 on the other sublattice, so that I get antiferromagnetism. Okay? Everyone see how I get here? Exactly what I did for the honeycomb. And then this coupling lambda is large, but okay, that didn't bother us in the honeycomb, so let's not bother by it here. So let's start from the metal, and R is positive, then this is still a metal, and fine, everything is good. Let's try to move toward the insulator. What happens? Well, so if you go into the insulator and R becomes negative, then phi will develop an expectation value. So I just replace phi by a constant. Okay, so now let me see what this term does to the band structure. This becomes a constant. I have C dot, the old band structure, and I have this new term. Okay, so to do that, I have to do a little bit of this is solid state physics. You have to get your hands dirty at this point and do a calculation with Brillouin zones and band structures. Sorry about that. But I'll try to do it just by drawing a few pictures. So what we are doing is we're taking you have the key question, what happened to the Fermi surface? The Fermi surface, the surface here, and you're putting in some modulation which oscillate as this wave vector k. So if you think of the Fermi surface, an electron will see that modulation. Let's do perturbation theory. Electron sitting on the Fermi surface will see that modulation get scattered by momentum k. So just reflect, that's just diffraction. So diffract off the modulation and acquire momentum k. So that it'll move it from this Fermi surface to this image Fermi surface. So what you notice here then, that there are special points right here and here and here where you're doing degenerate perturbation theory, where your initial and final points both have zero energy. And therefore, those are the points where you can open up gaps and you'll get what are called pockets. So these are the pockets that Suchitra was talking about, electron and hole pockets, which have rather small volume. And this is the simplest way you would change. This is the generic consequence of antiferromagnetism on a Fermi surface. It reconstructs it into small pockets. Notice the Fermi surface hasn't disappeared. There's still a Fermi surface there. It's made up of pockets, so it's still a metal. It's not an insulator. So this is one of the key differences on a honeycomb lattice. On a honeycomb lattice, no matter how small your antiferromagnetism, it became an insulator. Here, it's a metal to metal transition. It's a critical point in a metal involving change of the Fermi surface. And to me, that's the key problem, the key quantum critical point that needs to be understood. And I don't have a clue how to put that in ADS-CFT. I was only talking about the gauge field problem because it's much simpler. This is the problem I really want to solve. So I want this critical point between two metals where I reconstruct the Fermi surface, and I go from what's called the large Fermi surface to the pocket Fermi surface. Okay? And so the one interpretation of Suchitra's experiments, very beautiful experiments, is the size of the oscillation tells you the size of the Fermi surface, and it's clearly consistent with some small Fermi surface like this and not with this. At high doping, you see something like this. At low doping, you're seeing one of these small Fermi surfaces. And so one of the debates in the field is that pocket at the node, meaning is it the blue pocket, or is it at the antinode, meaning is it something like the red pocket? We don't know the answer to that. Because her experiment doesn't give any direct information on that. There's some indirect information which she was discussing, but we don't know for sure what the answer is. And that's one of the big questions that the field needs to settle. Where are the pockets? Are you seeing both or seeing one? And is it due to antiferromagnetism or charge density wave order, or to neither and something more exotic? This FL star phase, we have an analog of the FL star where you can reconstruct pockets without any order. These are very basic questions that experiments hopefully will resolve in the near future. Anyway, okay. So we've made actually a lot of it. So the analog of this critical point we've studied in this case, and let me just say a few words about it. So you go back. And the fact that there's such a critical point is certainly very clear in the electron dope cuprates, perhaps not so clear in the hole dope cuprates with the antiferromagnetism. At least the commensurate variety is only present at much lower doping. But in a system like this, it seems very clear that that's what's going on. You actually even see these pockets in photoemission on the electron dope sides. And so to understand the critical point, you have to really focus then on these very special crossing points, which are called hotspots, and write on a field theory for what happens there. And so if you zoom in onto one of those points, you get a field theory of fermions with Fermi lines interacting with another scalar order parameter. Okay, this is the kind of field theory you want, and it's got this Fermi, these V1 and V2 are these the different direction of the Fermi lines. Okay, so this is surely a non-Fermi liquid from everything we've studied about it, and it's also a strongly coupled problem. Everything I said for the fermion coupled to gauge field applies even more here. So for example, one of the things I showed you argued that if you did the vector 1/n expansion for fermions coupled to gauge field, you were forced to sum all planar graphs because of infrared divergences. That also happens here. What makes this much more difficult is that you have all these V1 and V2 are something that sit in a plane, so it's not rotationally invariant by construction. And so I don't even know how to begin putting such a structure in an ADS dual. So it's a problem like this, which is certainly more complicated than the problems I discussed, that we need to solve. And these are strongly coupled in 2 dimensions, even more strongly coupled than any of the problems I discussed. Okay, I think I will just end there, I suppose. So, you know, to 2-loop order, you get non-Fermi liquid behavior at that point, at the critical point, and all kinds of, and you even get superconductivity. But I think I'll just leave you with this action, and you can think about it. Homework problem, solve this one. Okay, thanks a lot.
Okay, we have time for questions.
What happens to Luttinger's theorem when you have this reconstruction?
It's perfectly valid. So there it's a very conventional thing. So the Luttinger theorem in a lattice is slightly modified. So when I discussed in the continuum, I said the volume of the Fermi surface equal the charge density. When you have a lattice, then the statement is that the volume of the Fermi surface equal the charge density mod 2. That's because when you have a lattice, you can always have a fill band, which is completely filled, which has no Fermi surface. And each filled band has 2 electrons per unit cell. So it's really only mod 2. So now when you have antiferromagnetism, so roughly speaking, if I compute the volume of this Fermi surface, of this large Fermi surface, let's say the volume of this large Fermi surface is A, then it turns out the volume of the small Fermi surface is A minus 1. You kind of lose 1. So you might worry about you losing 1. You can't lose 1. However, but in this system, you have doubled the unit cell. Meaning that you have 2 particles per unit cell, not 1. So the Brillouin zone is halved. So in fact, the Brillouin zone is a diamond like this, and 2 electrons per unit cell in the small Brillouin zone is exactly 1 electron per unit cell in the all Brillouin zone. So once you account for the mod 2 and the fact that the Brillouin zone halves, it actually does obey Luttinger's theorem. So there's no problem. If you got these pockets without breaking a symmetry, then you would violate Luttinger's theorem. And that you can do in some more exotic phases that I haven't discussed. But in this model, there is always a Luttinger theorem. I was discussing over lunch today. If some of you haven't heard about, lattices and Brillouin zones, well, think about root lattices and weight lattices of Lie groups. It's the same thing.
Is there an intuitive way to see why just changing the lattice from honeycomb to square causes such a big difference in the band structure? It's just points in one case and whole lines.
Intuitive, I don't know about intuitive. Well, one of the important differences is that the honeycomb lattice is not a Bravais lattice. Even though all sites are equivalent, it's got 2 sites per unit cell, even without any broken symmetry. So as a consequence, you get a matrix structure. You automatically get 2 bands. Now, under some values of parameters, so then you have to ask, so you have a 2 by 2 matrix, which preserves time reversal and spin rotation. Then you have to ask, can you get a point where the 2 levels are degenerate? So that means there are 2 conditions. The diagonal elements have to be 0 and the off diagonal have to be 0. So in somewhere in the Brillouin zone, you have 2 values of k. So the 2-dimensional space, there's always one point where they both vanish. So that's your singular Dirac point. So once you find a Dirac, you may not find any, but if you find one, then it's robust. You can't remove it because there's always a solution of these 2 equations. So it's some reasoning like that. So Dirac points are quite stable once you find them. It's simply a question of finding a 2 by 2 matrix with all the elements at some k are all 0. And near that direct point, there's a generic structure. It has to have a direct structure because of symmetry, again, time reversal and spin rotation and things like that. So the square lattice is a Bravais lattice, so there's no 2 by 2 matrix to deal with to begin with. So it can't possibly have a direct point, whereas the honeycomb could or couldn't. It just does have one. It's a 50% chance.
A related question: what are the more realistic lattices for unconventional superconductors or strange metals?
I mean, almost the square is definitely the best one to study. I mean, the pnictides are square, all the cupids are square. Strontium, deuterium, almost everything which is I mentioned is square or rectangular, pretty much. Honeycomb, we don't have any good honeycomb systems yet. I mean, there are some more exotic things which are deformed square, these Shastri-Sutherland lattices. But no, the square is the most important by far, fortunately. Yeah.
Do these pockets has something to do with D-wave superconductivity?
Not necessarily, no. I mean, so, okay, fine, I have a slide. So what is D-wave superconductivity? So the hotspots may have something to do with D-wave superconductivity. So these are the hotspots, okay? So what's special about the hotspots? Well, so if an antiferromagnetic fluctuation comes in, it'll take me from this hotspot to that hotspot, okay? So what's special about the hotspot is they're connected by the wave vector k. If I pick this point on the Fermi surface and move by wave vector k, I will not end up on the Fermi surface. I end up with some random point. But at these 8 points only, if I move by momentum pi, I'll end up with another 8 point on the Fermi, another hotspot. Okay. So now let me form Cooper pairs. So I form a Cooper pair between this person and that person. Now these antiferromagnetic fluctuations are most effective at the hotspot because there you're always scattering between low energy states on the Fermi surface. So this Cooper pair will scatter by an antiferromagnetic fluctuation to this Cooper pair. Okay, so now you look at the equation for PCS pairing due to antiferromagnetism. You put in all your Pauli matrices, and you find that it's attractive between the initial and final state, provided the gap changes sign. So that's the general requirement, that the gap should change sign when you move it by the antiferromagnetic wave vector. So for a circular Fermi surface, that's most natural for a D-wave thing. So it's, it's positive, positive, negative, negative, positive, positive, negative. That's the D-wave signal. But for the pnictides, you have a rather different Fermi surface and different topology, different wave vector k. Then you don't get D-wave, but you use the same argument, you get the right answer, which in that case is S plus minus in many of the pnictides. So yes, the pockets are indirectly connected to D-wave, but it's really more this picture. Because the superconductivity is present when the antiferromagnetism already, there's no long-range antiferromagnet in most of the superconductor. So the Fermi surface, underlying Fermi surface is probably the big one, not the small one.
Any more questions, comments? In the middle of your talk, you talked about the adjoint fermion coupled to Yang-Mills theory, taking the low energy limit of that.
Yeah.
There's another system that suggests itself probably at the same level of unsolvability, but consider adjoint fermions coupled to Chern-Simons theory.
Okay.
Now, this gives you a line of fixed points.
Yeah.
In the large
at zero density.
What?
At zero density.
Zero density.
Yeah.
Yes.
Yeah.
Okay. And so you get a line of fixed points labeled by a 't Hooft coupling.
Yes. Okay.
And roughly speaking, when you take this 't Hooft coupling to infinity,
Yeah.
it looks like it's more or less the same as your theory.
Which theory? Oh, this theory, the honeycomb lattice theory.
The theoretical model, which was
the Gross-Nouveau model. The Gross-Nouveau model. No.
Yang-Mills theory coupled to adjoint fermions. The theory
really?
we talked about 2 lectures ago.
Well, but I talked about that theory at finite chemical potential, but okay, at zero chemical
We
potential.
could take both of these theories at
I see.
fine. I was just wondering whether this would be a slightly more controlled system to study, since
I see. Really?
you have a fixed line.
Yeah.
You can do recoupling calculations and try to move.
That sounds very promising. I think this connection between Chern-Simons matrix theories and Yang-Mills is in your paper, right, recently. Okay, so I have to read that. It's possible. Yeah, no, that sounds like a very interesting idea. Yeah. I mean, anything we can say about that problem, finite density, I'm happy to, I'm sure will help. It's such a difficult problem. And it's just a baby version of this one, really.
Okay, well, let's thank Subir again for a very nice set of lectures.